And you should test the screen sharing. Aavishkar. Just go ahead.
All good. Okay.
Great. Let's see. Let's see. Aavishkar, do you have a particular audience you want to wait for?
No,
No. Okay.
I'm not waiting for anyone. You feel free to start whenever you're
Okay.
ready.
No problem. So I think we have many people already, so we can take a recording and start. Welcome, everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics Seminar Series. It's our great honor first to congratulate everyone for we just have a happy new year 2022, and this semester in spring term, the first semester first seminar, we have Aavishkar Patel from UC Berkeley, and he's also a Miller Fellow. His topic today will be metals with strongly correlated electronic quantum criticality and disorder interactions, Planckian dissipation, and scale invariance. I would like to remind the audience, please feel free to interact with Aavishkar by asking questions. You can raise your hands or you can just directly speak up. So let's directly welcome Aavishkar. So Svaga, Shukriya, thank you very much. Please take over.
Okay, yeah. Thanks for the introduction. So today I'm going to be talking on some work that I've done over the last few years on metals with strongly correlated electrons and transport properties of such systems and non-Fermi liquid behavior. Uh, and this work was done in collaboration with many people in the following papers here and also upcoming papers. And yeah, so I'd just like to acknowledge their help. Uh, so this talk's going to be on metals, and like from the solid state 101 class, we know that metals are they're states of fermionic matter at finite density. So you have a set of occupied states in momentum space and empty states, which are separated by a Fermi surface just from Pauli's exclusion principle. And property of metals is they're compressible, so you can continuously change the density or the number of electrons in the system as a function of some parameter like the chemical potential, and the compressibility, which is how much the density changes with respect to changing that parameter, is finite in the low energy, low temperature limit. It doesn't blow up or go to zero. And because you have this Fermi surface, there are a large number of gapless excitations that at every point of the Fermi surface you can take electron from the occupied state out into the empty state, and that defines an excitation that costs very little or zero energy, so it's gapless. and you have one for all the points of the Fermi surface. In general, schematically, you'll write like the Hamiltonian of such a quantum many-body system as a sum of like a kinetic term, which has a dispersion for as a function of momentum, and some interaction term for the electrons. In this case, I've written down a density interaction between electrons at different spatial points, r and r prime. This might sound like a pretty complicated system with large number of gapless excitations and stuff like that, but just with an ordinary density interaction, which could be like a Coulomb interaction, this thing is pretty easily solved. This is done way before in the 20th century, where if you write this gapless interaction in terms of a Hubbard-Stratonovich field, then that emergent bosonic field, it gets screened by the charge fluctuations through like this kind of vacuum polarization diagram, and because of that screening, that field, the emergent bosonic field that mediates interactions between fermions, cannot fluctuate very strongly, and fermions interacting with such a gapped, weakly fluctuating field essentially stay non-interacting and don't change very much. So they become what are known as renormalized quasiparticles, and so quasiparticle is a long-lived, weakly interacting additive excitation, which behaves pretty much like the original electrons in the system, except they have renormalized masses and velocities. And what is important is that this quasiparticles can decay with some decay rate because they interact with each other, but that decay rate is parametrically much smaller than the excitation energy, and especially as the excitation energy goes to zero. So that means that they become infinitely long-lived at low energies. So they are well-defined excitations. So what happens to your Fermi surface? Instead of having Fermi surface of non-interacting electrons, you now have a Fermi surface of quasiparticles, which are sort of like very weakly interacting electrons themselves, and that Fermi surface has got the same volume, so it contains the same density of charge as the corresponding non-interacting system. So the reason the decay rate of quasiparticles is very small is if you just do a Fermi's golden rule calculation with that kind of interaction term, you have to have a 2-in, 2-out process, and the golden rule tells you that your final states have to be empty, initial states have to be occupied. So you integrate over the available phase space because have a Fermi surface and the available phase space is related to excitation energies by a linear relationship near the Fermi surface, and you can just compute this integral and show that this decay rate gamma is of the order of the square of the excitation energy, which is either omega or temperature, and therefore since it's the square, it's much smaller than the excitation energy itself, and the damping rate is very small. Okay, so this quasi-particle concept is actually central to a lot of quantum many-body physics we do. As I explained, they're additive, long-lived excitations of our ground state. So you have a ground state, and you can just write an excited state schematically as acting creation and annihilation operators of quasi-particles on the ground state. And in Fermi liquid, you had these Fermi surface of Landau quasi-particles, but there are other kinds of quasi-particles all over the place in various condensed matter systems, like Bogoliubov quasiparticles in superconductors, and there can also be quasiparticles in a very non-trivial basis, very different from your free electron momentum space basis, like in systems like spin liquids, where they are some uh, complicated emergent quantities. But the point is that you can still write down your excited states in terms of additive excitations of well-defined quantities over the ground state. And the ability to do this gives you the ability to write down the excitation energy of such a system in terms of the occupation numbers and alpha of quasi-particle modes that you excite, and then some corrections due to interactions of this kind. And the important point is you can write it as a polynomial in n alpha, and that get a good answer with just a finite degree polynomial in n alpha. And the consequence of that is that if you look at the many-body energy spectrum, you have pretty sparsely spaced low-lying energy levels in a finite-size system. So for in instance, we have a linear dimension n, then your excitation energies are spaced 1 over n at low energies. But we can also have situations where there are no quasi-particles. So you cannot write any single excited state in terms of just exciting well-defined quanta over a ground state. Although you can, of course, choose some basis and take an infinite superposition of quantities like what's on the right-hand side and write an excited state. But the point is you can't do it with just a single one. And also in such a situation, you cannot approximate energy as a polynomial in occupation numbers, and you don't have any notion of n alpha, which define occupation numbers of well-defined excitations. And such a many-body energy spectrum in such a system is got densely spaced energy levels at low energies, which at finite size the spacing becomes smaller than just 1 over n. So this talk's going to be about non-Fermi liquids, which are non-quasi-particle systems, but ones that still have a Fermi surface and that encloses some charge density. So that can occur where you have this again the schematic Hamiltonian for a metal, but your electrons interact with a gapless bosonic field, not a screened Coulomb interaction anymore. And that gapless bosonic field can usually come about from, say, a order parameter at a quantum critical point, which is very strongly fluctuating, or in more exotic cases, it can come out of an emergent gauge field. And this is especially true in 2 dimensions, where you can have strong fluctuations of this order parameter, but you still don't have all the special features of integrability that you get in 1 dimension. So in such situations, your gapless bosonic field acquires retardation from coupling to the fermions. So this polarization bubble, it doesn't screen it, but instead it gives it some dynamics which depend on frequency and momentum. And now you have strong interaction between the fermions and these gapless fluctuating bosons. And like what that does is it gives, if you try to use the naive quasi-particle picture, it'll give you a quasi-particle decay rate that is much larger, it's parametrically much larger than the excitation energy itself, which just tells you that your quasi-particle basis is too bad because you can't even define define a well-defined excitation. And so, yeah, this is one such example. If you try to compute with in 2 dimensions with this kind of damped fluctuating boson, you get this quasi-particle decay rate that's omega to the 2/3.
What would be the exponent in 3 decays?
There's omega log omega. So that's it's a lot better, but it's still parametrically much larger than omega itself. Okay. All right. So this kind of non-Fermi liquid system, which doesn't have quasiparticle, it still has the important properties of metals that it's still compressible. And it still has a well-defined Fermi surface in a translationally invariant case. And that Fermi surface can be defined as, the locus of points in K space for which the inverse Green's function at zero energy vanishes. And there's something called Luttinger's theorem, which tells you that that you'll still have this Fermi surface that encloses a volume equal to the total charge in the system. But there are no quasi-particle excitations, and you cannot parameterize your many-body energy in terms of this kind of polynomial. So such a strange state of quantum matter is still something that occurs in reality. And well, there are plenty of experiments on materials which have very strongly correlated electrons, most of which are at least quasi two-dimensional or layered or actually two-dimensional materials. And that I'll be focusing on 2 dimensions in this talk. What they do show is they show in many regions of their phase diagram, especially near putative quantum critical points, they have properties such as transport properties and specific heat, which don't agree with the weakly interacting quasi-particle Fermi liquid metal predictions. And one of the probably most famous property of such states of matter is they have linear in temperature resistivity down to very low temperatures. So at high temperatures, getting linear in temperature resistivity can occur through phonons, where the temperature is larger than the Debye frequency of the phonons. But there are experiments like this one on LSCO, where when superconductivity is suppressed, this T-linear behavior goes to very low temperatures. There's also this very nice recent experiment on magic angle twisted bilayer graphene, where you have linear in temperature behavior over 3 decades of temperature. So it goes all the way down to 40 millikelvin and all the way up to 40 Kelvin. And this is at odds with what you would expect for a weakly interacting Fermi liquid, where you get a T-square resistivity, which just comes from the T-square scattering rate of the quasiparticles and from the processes that contributing to that T-square scattering rate that can relax current and momentum. And also this T-linear behavior is accompanied often by large specific heat that is seen in many materials where the specific heat doesn't have the linear in temperature behavior that you would expect from a Fermi liquid. So, my challenge has been to first come up with a systematic theoretical description of non-Fermi liquid states of matter, and then use that systematic theoretical description to compute things that can be measured in experiments and try to figure out how such things might originate. So the problem with the theoretical description has been that if you just try to do a naive perturbation theory in your fermion boson interaction, you cannot consider that coupling G to be small by any means. There have been many tricks that have been played, but which usually you cannot access the low energy limit in 2 dimensions with a completely local initial Lagrangian while retaining all the interesting physics of strong boson damping and quasiparticle description. And in a very quick way to see why G is too cannot be considered to be small is.
Could you go back? What do you mean by local here? Local in which space?
In position space. So if I Fourier transform S int here, then these three are all at the same space point. If I Fourier transform S phi, then it's just phi of r grad square phi of r. And so yeah, you sort of start with an action that's local in position space. So I mean, there have been tricks where they modify the boson dispersion to not q square but mod q, or some q to some other power, but then the boson's not local in position space anymore. Does that answer your question?
Yes.
Okay, thank you. Right, so this, this perturbation, naive perturbation theory in G is uncontrolled, and because G is large, you can just see that from the single particle self energy, which is G square omega to the 2/3. So no matter how small G is at small omega, this omega to the 2/3 is much larger than omega itself. So you're always going to get a decay rate that's larger than the excitation energy itself, and at low enough energies, even though G is small. And there have been some tricks with vector large N expansions, which tried to suppress this omega to the 2/3 by an additional factor of 1/n. But in that was already sort of not a very great idea, because you're trying to suppress something that gets large at low energies anyway by an additional parameter, and then take the low energy limit. And Sung-Sik Lee showed that was problematic, that you could always add up higher order diagrams and get similar contributions. And that didn't work. So, to build a solvable theory for this kind of stuff, I'll first describe something called the SYK model, which I'm sure a lot of people here know a lot about. So the SYK model deals with, it does create a state of matter with no quasiparticles. It's a non-Fermi liquid, but it only is in 0 dimensions, I mean 0 spatial dimensions. So what it consists of is a large n number of fermions at the same point, but with different flavor indices. And you have this Hamiltonian, which is all-to-all random interaction, where the couplings have 0 mean and some finite variance. And you take this large n limit before the low energy limit. That what that does is you get a state where this randomness self averages, and if you try to compute like the Green's function. In this case, just doing Feynman rules on this interaction gives you a self-consistent relation between the Green's function and the self-energies, which is of this form. And importantly, the solution of such an equation is the very weird power law Green's function, where at zero temperature it's 1 over square root omega. And that's really not got any quasi-particle structure to it at all. And you can solve this model on a computer as well at finite size and look at the low energy spectrum, and you see that there's a very dense set of states with no 1 over n spacing. So it really doesn't have quasi-particles. And this relation between the self-energies and Green's functions can also be derived through the path integral, where you average over all these random couplings, and then you can define your self-energy as a Lagrange multiplier field that enforces a relation between the Green's function and its definition. After integrating out the fermions in a large n limit, you get a saddle point, you get an action, and you take the saddle point of that action with respect to G and sigma, and then that gives you the equations for G and sigma on the previous slide. Okay, so this basically is a very different way of taking large n limits from what people used to do previously, where strong coupling physics and destruction of quasiparticles is retained in the large n limit. You don't try to suppress the effects of interactions by making n large. And it still allows you to solve exactly for certain quantities, like the Green's function and the self-energy. So, yeah, I mean the models I was talking about are non-Fermi liquids. They have fermions interacting with some gapless bosonic fields, whereas the SYK had like random 4 Fermi interactions. So if you want to apply like SYK kind of techniques to problems that I was talking about initially, we'd need to have a random interaction between fermions and bosons. So, something schematically like this, where you have your random coupling is now a random Yukawa coupling. So there have been various works over the years that dealt with such situations, starting with one in 2018 by me and Subir on where the fermions had some random coupling, random Yukawa coupling to gauge fields, and then there were other works like this one in JHAP where there was instead of a gauge field, there was random Yukawa coupling to scalars, and then there were works by Yuxuan Wang, Ilya Esterlis, and Jörg Schmalian, where they looked at this random Yukawa coupling with scalars and studied some superconducting instabilities in 0+1 dimensions itself. And then there was another one here by Kim, Kao, and Altman, where they look at different distributions of GIJK instead of fully random distributions. And the kind of central feature of all these papers listed here is that one again gets exact Schwinger-Dyson equations that relate Green's functions and self-energies, but now you have two sets. You have a Green's function and self-energy for the boson. So you have a relation between pi and which is the boson self-energy and the boson propagator, and sigma, the fermion self-energy and the fermion propagator and boson propagator. So this form of Schwinger-Dyson equation is familiar in the condensed matter world, and people just call it RPA, RPA Schwinger-Dyson equations, or RPA approximation. And that can come out of a SYK model of fermions interacting with bosons. So obviously, what we want to do is try to all that was in 0+1 dimension. So we want to try to do this for 2+1 dimension systems. So what we do is we promote now both fermions and bosons to large n number of flavors, which is different from previous attempts at vector large n approximation at expansions where only you had n fermions and only one boson, but now you have n fermions and n bosons. And then we keep the same kinetic terms for the fermions and the bosons in the action, but we introduce these flavor random GIJK Yukawa couplings, which have zero mean and have some finite variance that's appropriately scaled with 1/n. And then you can do the same kind of path integral average over GIJK or just use the Feynman rules. And in the large n limit, like in SYK, that should be equivalent to self-averaging. And the result is you get a saddle point with solutions for fermion propagator, boson propagator, fermion self-energy, and boson self-energy, which satisfy RPA equations. And just like in SYK, and unlike in many previous other attempts, the large n limit is taken before the low energy limit, and that's a very important feature. So when we
Aavishkar, can I ask a question?
Yeah.
Yeah, so to return to the last point that you just made, so I'm glad you emphasized this. So does this mean that in terms of applying the results of this large n limit to a finite n model, that you should only expect this large n approximation to capture the physics above some energy scale?
Yeah, I mean, yes, I'd agree with that. Like the lower you want to go in energy scale, the more 1/n corrections you would have to start including.
Mm-hmm. So the true asymptotic low energy physics of a finite n model is complicated to access within this 1/n expansion. Is that a summary?
Yes, yeah, I mean, it is, you can say that. Yeah. It might be a very, very, very low energy scale where things could, become very complicated. But yeah, I agree with that.
Yeah. Okay, great. Thanks.
Yeah. So yeah, we have our RPA equations, and so we have this boson which can have some mass, but if you can tune this system to a quantum critical point where m goes to 0, and then when you solve these RPA equations, which are exact in the large n limit, you get this in 2 dimensions. You get your fermion self-energy in the non-Fermi liquid of omega to the 2/3 and overdamped boson. And importantly, both this sigma and pi are order 1 quantities, and they're not suppressed artificially by any 1/n or something. So you get the strong coupling non-quasiparticle physics at exactly in this at infinite n. Okay, so yeah.
Avinash, if I can interrupt you for just 1 second. When you're talking about suppression of omega to third term, isn't it just a normalization of self-energy? I mean that omega to third is multiplied by something with dimension omega to 1/3, and 1/n goes there. So you express everything
there is no 1/n in this.
But it depends how you define overall prefactor.
Yes, the overall
something with dimension omega 1/3.
Yeah, so it's g to the 4/3 omega to the 2/3 or something. That's the That's this next slide right here. So here
Right,
you
right.
have
But
g
what
to
I'm
the
asking is this: if suppose that there is a factor one, you construct theory in different way, and the factor 1/n appears in the prefactor, then you still express everything in terms of some scale in the theory, and then 1/n just give you some overall scale in the theory. The theory still remains the same.
Yeah, so in that case, you have to your energy scale has to be larger than that scale set by 1/n uh, for for that to be a sensible result, right? Because you can't make that small in 1/n below some energy scale.
It's true.
That's
yeah. Yeah. Okay, that was just a remark. So continue.
Yeah. Right. So over here, we also, you can do this at finite temperature. Finite temperature is a bit funny, but it is what it is that you have one term here that has, this kind of two-third with some mutual scaling between omega and t that's given by such a function, and then you have a separate piece that comes purely from the purely thermal fluctuations of your phi field, and that's like in 2 dimensions is t to the 1/2 up to some log correction, but it's not t to the 2/3. But that comes out of solving the saddle point equations at finite temperature once you take into account effects of self interactions between bosons, and I'll mention more about the self interactions between bosons later. So yes, in this case you have order 1 self energies and strong coupling physics down to zero, very low energies at infinite n. But it's also possible to systematize 1/n corrections in this kind of language, because you have a saddle point, you can always write down fluctuations about the saddle point and then get an action for those fluctuations. And those fluctuations are come in only at 1/n order. And like those familiar with the SYK model would know like that the fluctuations in SYK were special. They had the Schwarzian action related to time reparametrization symmetry, but one doesn't have such special features here. There's no particular mode of fluctuations that just dominates over everything else like the Schwarzian did in SYK, and you just have instead a more naive picture where your fluctuation fields delta g sigma d pi, they have some mutual interactions between them, and then you have these vertices between fluctuation by local fields, and you can compute using those vertices and Feynman rules for your fluctuation by local fields. You can compute like what the correction to G is by looking at the expectation value of delta G, which comes from like tadpole diagrams like this, or you can compute corrections to other quantities by doing kind of diagrammatics and with these vertices and Feynman rules. And yeah, so that's that you end up having to do all kinds of horrible integrals, which we didn't do, but in principle the calculations can be done, and we can understand at least maybe do a few orders in 1/n what corrections look like. For example, we'd expect that the fermion gets an anomalous dimension that's order 1/n. That might it would be interesting to see how significantly those corrections affect the true low energy physics at finite n, like what Senthil was talking about. So even we can going back to n equals infinity, there are still many other interesting things that can be done. One is that if you, depending on the form of these GI-JK interactions, whether they're even under inversion or odd under inversion with some form factor, or whether they are real and therefore preserve time reversal symmetry, or they're complex and therefore break time reversal symmetry, you can have superconducting instabilities, or also charge density wave instabilities, even at n equals infinity. And one can search for those instabilities by looking at the renormalization of pairing vertex, for instance, which can be done exactly in a large n calculation by summing up ladder diagrams. And depending on the various parameters you can put into this theory, like the number of boson flavors versus number of fermion flavors, or the type of GI-JK, you can get stable and unstable regimes for both superconductivity and charge density wave orders. So for example, you can have two different types of bosons, one which mediate attractive interactions between opposite points on the Fermi surface, one which mediates repulsive interactions. And if you have real random GI-JK that preserve time reversal symmetry, there is if you look at the ground state at zero temperature, one does find a regime where if your interactions are sufficiently attractive, what happens is that your pairing bilinear picks up a complex scaling dimension, and that indicates that you have a superconducting ground state. And on the other hand, if you're dominated by repulsive interactions which repel points on opposite points on the Fermi surface, that can lead to density wave instability with ordering wave vector of 2kf. And that occurs again when the repulsive interaction is finitely strong, and that creates an instability. So we computed many more details of all these things in the paper that has been referred to at the bottom of various slides. Okay, but since I talked a lot about transport phenomenology and T-linear resistivity, I would like to try to understand those things and how to get there from the kind of models that I have shown you. One major problem with getting any kind of non-trivial transport behavior is that these are translationally invariant models, and you have a finite charge density and conserved total momentum, so you really can't excite a current without exciting momentum. So to degrade the current and to relax momentum, you need some process that relaxes momentum, like having Umklapp scattering, or just having a non-translationally invariant system where momentum can relax just due to collisions with disorder. And there have been some other proposals on how to get non-trivial transport behavior within a translationally invariant system itself, but I will be focusing on the route where I will use disorder in order to get non-trivial transport behavior and temperature dependencies of DC conductivities. Right, so okay, this is again just a quick slide that talks about strange metals, which are these phases that occur above putative quantum critical points in different correlated electron materials with T-linear resistivity. And there are really lots of examples of this way these days. And another special feature these things have with in addition to T-linear resistivity is that that if you just try to your density of carriers in the system, so you plug your resistivity into the Drude formula, and if you use the effective mass that you can measure through quantum oscillations or specific heat in a nearby Fermi liquid phase to the strange metal, then that effective mass is renormalized by electron interactions and and it's much larger than the bare band structure electron mass itself. So when you use that kind of effective mass, you get a transport scattering rate that's linear in temperature with it, and it's universal in the sense it's kBT over h bar times some over whatever temperature ranges they can measure and stuff like that. The coefficient of proportionality is order 1 number. And some people like to call that Planckian dissipation. So we have T-linear resistivity. Let's first see what really can we do to get a T-linear single particle scattering rate. So that T-linear single particle scattering rate was understood phenomenologically back in the early 90s as arising from the fermion scattering of some bosonic fluctuations that are momentum independent and have this logarithmic susceptibility. And if you did that at finite temperature, you'd get a imaginary self-energy that gave a T-linear scattering rate. But there was how one gets a model for this and how especially something like this can arise at a quantum critical point in a controlled calculation was not very clear. And furthermore, one would have to understand why this T-linear single particle scattering rate is equal to a T-linear transport scattering rate. But this, it seems to be a very good proposition or good ansatz for self-energies of fermions, because there are various experiments like RPEs on some materials, like in this paper it's on some pnictide kind of material, where they do find that there are regions of the Fermi surface where there's this, in RPEs you can look at the energy dependence of the spectral function, and you can infer from the peak with what the scattering, the self-energy of the electron scattering rate is as a function of energy, and then they find this marginal Fermi liquid behavior. It's proportional to omega, for instance. So, how would you get something like this in a model, and how do you translate it to a transport scattering rate? Is what I'll be talking about in the next several slides. So, yeah, as I mentioned, I'll be using disorder in order to relax currents and momentum. So the most naive form of adding disorder to, say, our model for quantum critical metal is to add a random potential term V of R, because we like SYK like large N limits. We can make it Vij random coupling with N being large. And if you just do something like this, then it does change the low energy structure of the bosonic fluctuations at the critical point, because now the boson is damped by fermions that have a different low energy behavior because of this random potential. So you get this different kind of boson propagator where your damping is now independent of momentum. It's just mod omega instead of mod omega over Q. And this leads to this kind of marginal Fermi liquid contribution to the fermion self-energy, in addition to, of course, the residual constant that this kind of impurity scattering will provide. However, because the fermion boson interactions are just coupling fermions to small q bosons, because they're translationally invariant. The interaction part is translationally invariant, that is. This marginal Fermi liquid self-energy arising for the fermions is basically just forward scattering. And as such, if you compute properly the current correlation function, including systematically all the terms in your large N expansion, then this forward scattering piece will cancel out, and you don't get a marginal Fermi liquid or T-linear contribution to the resistivity. Or resistivity to leading order is just a constant coming from the residual impurity scattering rate, and there's no T-linear correction. So the trick that I play is to consider the possibility of having interactions that are disordered, not just the potential term. So like we had this Gij coupling that was uniform in space, where we can offset it by a spatially random part, G prime Ijk. And yeah, I mean, you can say G prime is not bigger than G here on this slide. So what does that do? Again, because you have this potential term giving you a residual scattering rate for the fermions, you still get this kind of boson propagator. And in two dimensions, both your G and G prime interactions give you this mod omega form. And because of that, that boson propagator coupling with fermions, either through G or G prime, or through both G and G prime, you get marginal Fermi liquid contributions again to the self-energy, and of course, in addition to the residual scattering rate. But now this marginal Fermi liquid contribution has two pieces: one that comes from the clean part of the interaction, one that comes from the disordered part of the interaction. And both of them are marginal Fermi liquid, but the disordered part of the interaction is not forward scattering, right? Because it doesn't conserve momentum, so it can scatter you from one point of the Fermi surface to another point of the Fermi surface very easily. And that relaxes current, that relaxes momentum because of not having translation invariance. And if you do the calculation for the conductivity now, you actually get a T-linear correction to the residual resistivity. And furthermore, you find that the slope of this T-linear correction is independent of the residual resistivity. The residual resistivity depends on V square, and the slope of the T-linear correction comes from G prime square if you do this computation. So that's actually, that's something that people have noticed in experiments, at least with the available data, that can try to damage their samples and increase the residual resistivity. The T-linear correction the slope of the T-linear correction doesn't seem to be affected all that much. So it indicates that there are different mechanisms, like what this model is doing. Right. And furthermore, this marginal Fermi liquid susceptibility that's coming out over here is not coming through any kind of local criticality. It's not that we have some local bosonic mode which the fermions couple to. The bosons also live in two spatial dimensions. It's basically the coupling between the fermions and the bosons and the critical sector that's local, rather than the critical sector itself being local because of this random structure of G prime.
Can I ask you a question? I mean, why do you need this random V? Can you
I don't.
Yeah,
I don't.
Can you set the Vij to 0? Right.
Yeah,
then you still have a residual. Then you still have a residual resistivity from the G prime term, right?
So yeah, just let me do the next slide because that's it's exactly your question.
Yeah. Okay.
Yeah. Right. So let's say we set this V to 0. So we only have a G and only have a G prime, right? So now one can go through the RPA equations and you get your at the quantum critical point, you have a different structure for the boson, in which now you have damping that's both the mod omega over Q damping that's coming from the clean interactions and an additional mod omega piece that arises from the disordered part of the interactions. So, I mean, obviously at low energies, mod omega, low energy long wavelength, mod omega over Q is much bigger than mod omega, right? So, if you look at the fermion self energy, the leading term that shows up is controlled by this mod omega over Q, so you get omega to the 2/3. However, you also have this G prime interaction, which the mod 2/3 just comes from the clean interaction of fermions and the bosons, but you also have the disordered interaction, which generates a marginal Fermi liquid correction. It adds on top of this 2/3. And now there's no residual resistivity piece, at least in this large N calculation, where your Vij, because Vij is 0, you don't directly get it. If you were to go to 1 over N corrections, like I mentioned earlier, you might be able to generate some small residual resistivity, but it's parametrically suppressed by 1 over N. And so there's no residual resistivity, and you have a marginal Fermi liquid correction to the fermion self energy. Now that correction is omega log omega, but that's arising from this disordered part of the interaction that can degrade current and momentum. So while the 2/3 comes from forward scattering and doesn't contribute to the transport, the correction does. Right? So that the leading irrelevant correction is what contributes to transport, and you get a T-linear resistivity up to some weak log corrections with no residual piece in this case. So you have disorder, or because the disorder is occurring in a channel that's a higher order operator rather than just a potential term, you don't get a residual resistivity. So it's not that that disorder always has to give you residual resistivity in any case. It doesn't in this particular case. It's just a counterexample.
So, I mean, just to understand you completely, you're saying that resistivity is linear in T, but if you look at RPS should give you omega to third with some extra corrections, right?
Yes, correct. Right. But if you had this Vij, then both then RPS will also give linear omega log omega. That's if the thing on the previous slide where you had this term, then the RPS would give you constant plus omega at low enough energies.
Right.
In this case, because there's no residual, the 2/3 comes back.
So can I'm a bit confused by this. Maybe you're going to say that it's because of log n. So with disorder, the Landau damping will be cut off at Q of order 1 over the mean free path or something, right? So the omega over Q, you don't expect it to survive the presence of disorder.
You mean when Vij is 0 or when Vij is non-zero? Because when Vij is non-zero, exactly what you're saying happens, and then you don't get omega over Q at low energies. When Vij is 0, like maybe some 1 over n correction at some order generates a Vij, and then that omega over Q gets cut off at some energy scale that is small in 1 over n. Yeah.
I see.
Is that a good enough answer?
So, I see. Okay.
Okay.
Actually, related to that, so the slope was linear t. You said this independent of the residual resistivity, which in the log n limit comes from this Vij. But the slope does depend on the disorder strength, right?
Sure, it depends on G prime square, which is the variance of the disorder. Yeah.
Right. Okay.
So the question is, well, it's a different kind of disorder, right? So the question is this irradiation of this sample, is it generating, seems to be generating V terms, not G prime terms. The mechanism for G prime could be different. Yeah.
Okay.
I have another question, related question. So you said that this omega over Q, if you take the next 1 over n correction, Q may be replaced by 1 over n, right? Because there may be a next order correction. So that means that n actually goes up in the numerator. So you actually multiply by n. And would that lead to a breakdown of large n expansion?
No, I didn't say that Q itself is replaced by 1 over n. I just said that that there'll be another term that
there will be a gamma term, which is order 1 over n.
Right.
So for small q, that will be leading, and you have an n upstairs.
Yeah. So
I mean, this is a similar mechanism where the Sung-Sik Lee was arguing that the 1 over n expansion breakdown. I think something like that.
No, I don't think it breaks down in exactly that way. But what happens is that if you now add the 1 over n corrections, there will be a lower energy regime where you'll be dominated by a propagator that has this form, right? So I think you still get an order.
Gamma is all over n.
No, I think you still get.
You still get a
scattering.
Sorry. Another way to say it, what Aavishkar is saying is that in order 1 over n, V will be generated. There'll be a V which will be about 1 over n or something. And then you use the same theory with the bare value of V, which is about 1 over n.
I'm sorry, I couldn't hear you. Can you repeat, please?
Sorry. Okay, I'll let Aavishkar answer. All I'm saying is another way to say what Aavishkar is saying is that the V could be about 1 over n.
But
if you set V to 0, it'll normalize.
Where there's no V.
Right, but no, you have to consider the full theory, and V will get generated at order 1 over n. That's one way to think about it. It's the same theory, except that the bare value of V is order 1 over n.
Okay, yeah. And so wouldn't that enter as a denominator then?
No.
No?
No, I think no. There's no like Sung-Sik Lee like problem. I think you just get
All right.
I mean, maybe I can just rephrase just to make sure where we are settling on. So the V that's generated is of order 1 over n, and the mean free path that cuts off the Landau damping, that's presumably proportional to V squared or something, right?
Yeah.
So then the gamma in this expression is of order 1 over V squared. right? And V is of order 1 over n to some power. So that I think is the concern.
But you still get omega term in the propagator. Its coefficient will be different.
Yeah, I mean, yeah, sure. You get, right, you'll have like a 1 over, yeah, we have omega with over n or something, right? That's what.
Omega times n, I think is the.
It's omega times n, most likely.
Yeah. But yeah, if you look at the fermion scattering of that because it's 2 dimensions and you integrate over momentum, that it ends up in a log. Right? So it would be log some UV cutoff over n over there, and there's no 1 over n out front in the self-energy diagram.
No, I was concerned by not the gamma prime term, but the omega over q term, where the q, in this limit would have a 1 over n.
No, yeah, I don't think you have
so. I mean, if you say so, it takes some. I think it takes a little investigation to be sure. But if you say so, it's fine.
Yeah, like I've not done the full calculation yet, but I think the scattering of the boson will be fine at least the things we're talking about will be fine. What just happens is you will have an additional diagram of self-energy, which is not of the form that we are seeing, which can be written as an effective V, as Subir said, and that V is order 1 over n. So you get a constant piece that's order 1 over n in the fermion self-energy plus some order 1 stuff that comes from scattering of the boson. That's what I think happens. But yeah, we'll do the full calculation someday. Is that yeah? Fine. So okay.
Yeah, fine. Please go ahead.
Okay, thanks. So we have these disordered interactions, and I talked about them. There's also an extreme case in which you have fully disordered interactions. So you don't have this Gij at all, and you only have a G prime. So what does that do? So I'll also use that as an opportunity to explicitly show calculation of temperature dependencies. So say we have a G prime here in this term, but no G. You have action for fermions and bosons, and there's also explicitly showing you now action for boson self-interactions, which in the large n limit, people will recognize this as the ON nonlinear sigma model, which is a controlled way of putting in boson self-interactions at large n. And if one puts these things together, you get your Elie-Ashberg equations, and you have this tuning parameter in the ON piece of the action that can give you a quantum critical point. And one can also take into account all the thermal fluctuations and everything with this kind of setup. So yeah, I mean, we do this. Now we have only G prime, right? So what happens is, well, the boson's 2-dimensional, electrons are 2-dimensional. But the electrons couple locally to the boson fluctuations at large n because you have a disorder average line here, and you have to integrate over momentum for both the electron and the boson lines here, right? And that because of that integral over momentum in 2 dimensions, you couple to something that has log fluctuations. And once you take into account the effect of the self-interactions of bosons and everything, you get a scattering rate that is T log t. right? So it's got a weak correction that you can compute exactly at low temperatures in this setup. It's not log, it's actually log. And yeah, so you have this G prime is random in space. It kills current and momentum, so it also gives you the transport scattering rate, and that will manifest in this case, very simple computation for the current correlation function. You only get this diagram, and everything else, because of either the large n limit or the isotropy of the scattering rate through a G prime process, doesn't appear. And you literally just have to compute this bubble diagram, which gives the equivalence between single particle self-energy and transport scattering rate. And this fully disordered G prime situation, it also gets you kind of close to this Planckian limit, because if one looks at, you have only G prime, right? And you look at how the effective mass is renormalized a little away from the critical point. You can either go away from the critical point using gamma, tuning it away from gamma C, or you could apply some thermal cutoff to take you away from the critical point. Or one gets a mass renormalization that, as long as you're at your dimensionless coupling here is strong, one has this kind of mass renormalization defining the scattering rate in terms of effective mass. Now, a scattering rate in the critical fan in terms of effective mass gives you this kind of thing. It's order 1 kVt over h bar times these logs, right? You have a log t over log t, which is with all the non-universal stuff is within this log, and that's a reasonably slowly varying function. I mean, if you have a factor of 10 discrepancy in G prime between two different materials, then this logs acting on that factor of 10 is only going to give an order 1 change in the prefactor of kVt over h bar. And this happens when you have the fully random interactions, because a special feature of fully random interactions is that your G prime is the same interaction which contributes to effective mass renormalization and to transport scattering rate. However, if it was G plus G prime, it's not fully random, then your effective mass renormalization comes from G as well as G prime, but your transport scattering rate comes only from G prime, right? So then the 1 over tau star will depend on the ratio just outside as a prefactor of some power of G over some power of G prime. So that's a much stronger dependence on non-universal factors. So this full randomness actually quite interesting based on stuff that's observed in experiments. Okay, so yeah, so there are also some other versions of these problems that I considered where in this paper, where one can have 2 bands of fermions, not just one, and have some Kondo hybridization field between them, but that field has thus kind of random couplings. And when you have that kind of scenario, then one has to deal with Joffe-Larkin rules and other constraints that come about because you have emergent quantum numbers associated with like the F band, and that's a whole another work where you can describe some transition between having a small carrier density or FL star and Fermi liquid with a large carrier density. You can compute like the Hall coefficient and see how that evolves across the transition. It changes from one Plateau value to another as you hybridize two fermions. You can and again with these random interactions, you can get a marginal Fermi liquid strange metal in the quantum critical fan between them. And there are also some interesting temperature dependencies of the Hall coefficient that can arise within the critical fan itself, some non-monotonic dependencies, for instance, and enhancements that come from having charged bosons, and as well as weird features in the inelastic scattering rate of the fermions. So that's how that was done in this paper. One interesting thing in this Kondo lattice scenario is that if you have, because your bosonic fields are complex, they hybridize C and F, so they have to be complex. They can't not hybridizing C and C. They're not particle hole symmetric, right? Because a complex boson is a propagator that can depend on omega, not just one omega. And what that does, which is kind of very funny, but also potentially very interesting, is in such a scenario, you can have a fermion self-energy or scattering rate that is asymmetric in plus minus omega. So it's a marginal Fermi liquid, all right, but the slope with omega is different for positive and negative frequencies. And so that's what this phenomenological paper here calls that a skewed for self-energy or skewed scattering rate. And a consequence of having this skewness is that there's an asymmetry between particle and Hall excitation. So that gives you non-zero and like non-vanishing thermoelectric Seebeck coefficient, even as temperature goes to zero with a Fermi surface. Whereas otherwise such a coefficient without this asymmetric scattering rate, such a coefficient would vanish at zero temperature as some order interaction over or order temperature over the bandwidth of the non-interacting fermion system. But over here it doesn't vanish as temperature goes to zero. Okay, so yeah, the last part of this talk would be trying to understand and maybe have some ideas on what's going on with these strange metals, because they can have T-linear resistivity, as I mentioned, over very large ranges of temperature. So there are certain samples like this LSCO where you can have very small T-linear resistivity at low temperatures, and it goes up to very large values, which are larger than h over e square, which is called the Joffe-Regel value, where the classical mean free path of the electron becomes comparable to the lattice spacing. And it keeps the same slope even at low temperatures, where the classical mean free path is much smaller than the lattice spacing, and at high temperatures where it's larger, the slope stays the same. And there's another very nice piece of data here where, apart from the superconductivity, the extrapolation of this line just continues all the way down to zero as you go to zero temperature. So one again has the same slope over a very large temperature range, going from both the good metal, where this value is less than Joffe-Regel, and the bad metal, where it's larger, right? So it tells you that something that, because you would expect that this bad metals and good metals are very different things, that there's some kind of there's something that's still shared between the two, right? If the slope has to remain the same, and that there's some kind of scale invariance in the system, even though there are all kinds of crossovers occurring between the good metal and the bad metal regime, there's something that doesn't change. And so the question is, can we make this kind of scale invariance explicit in a quantum many-body picture? And so we did find that if you just deal with the Kuba formula and make a few simple algebraic manipulations, the Kuba formula where I is the current operator gives the DC conductivity as this expression where M and N are your quantum many-body states, and En are the excitation energies. So one has this expression where Z is the partition function. Partition function can be written in terms of many-body density of states G of E. Right? So one can then do some multiply and divide and pull out the partition function, right? And with defining this kind of piece to be a function f of E in the microcanonical ensemble. So then what that does is it makes your DC conductivity this form, where now you have a density of states and this f of E. One can see now if we have this f of E is independent of energy, right? You just have this expression here, which is the same as the partition function, and just cancels out. And then what one gets then is sigma dc is the constant value of f of E times pi over temperature. So it's exactly 1 over T, which would mean that the resistivity, which is 1 over sigma dc, is perfectly T-linear. And it's also true the other way around. If you have absolutely perfectly T-linear resistivity, then this quantity that you can compute in the many-body microcanonical ensemble is invariant with respect to many-body energy. Right? So that seems to indicate that there is a relationship between perfect T-linear resistivity and some kind of energy scale invariance as encoded by this function of the current operators. And one can't do that with like T-square resistivity of some other power of T, as far as I know. So we're still trying to understand where this thing might come from, but it's interesting that it exists, and we've been looking at numerics on various systems, like systems with SYK dots, and we find that it's roughly, at least within all the kind of finite n effects, it seems to at least roughly be behaved. Like this SYK dots with weak tunneling between them are a system that's known from exact large N calculations to have T-linear resistivity, both at low temperatures where this tunneling between the dots is very weak, so that's effectively zero. But one can have temperature much smaller than J or temperature much larger than J, and you still have T-linear resistivity with almost exactly the same slope. So that would indicate that this F is energy invariant quantity, and as we increase the value of N, there definitely seems to be a trend that it will end up within this range defined by these lines, which are the analytical obtained values for low temperatures and high temperatures. And we've also tested this in like the so-called trivial high temperature regime of like Hubbard models where you get T-linear resistivity, and you do find that this f of E as a function of the many-body energy is roughly invariant. We're still working on this, and you're trying to decompose the current operators into different pieces and see where this energy scale invariance actually lies, and we do have upcoming work on that, and I'll be happy to talk to people in more detail about it offline in that case. Okay, so this brings me to the end of the talk. We have this, what I've basically demonstrated is we have this, we can take these SYK like large N methods, and you get solve a lot of things self-consistently, both in systems with disorder and without disorder. We can compute transport quantities, we can look at instabilities, or even one could even study phase transitions by doing something by looking at the exact nonlinear Aavishkar equations that would emerge, for instance, instead of just doing the instability analysis that I showed you. So obviously, one goal is to understand how significant are these 1/n corrections in more detail. So how well does large N agree with finite N numerics? Also, one could think about doing QMC simulations in that case for like say metals with disordered G couplings like I talked about, and see how well does marginal Fermi liquid behavior survive, or what energy scale does it survive, and maybe go to the next step and add 1/n corrections to the saddle point, and then compare that with numerics and see if there's a discrepancy in the original case, does it improve things? Furthermore, one can do a lot of non-equilibrium stuff with these large N-Schwinger Dyson equations, because they can just be solved on the Keldysh contour instead. So one can, say, look at signatures that would be useful for non-equilibrium experiments, like transport beyond linear response, or maybe in a non-equilibrium ARPES experiment. It would be interesting to see how the dynamics of the fermion spectral function is affected by this bosonic bath. Or one could look at like the order parameter dynamics across phase transitions, etc. And there are also interesting directions I'm thinking about it, like computing low energy spectra of non-Fermi liquids for various models using large-scale exact diagonalization. And like, how does one come up with some parameterization of excitations that, just like you have quasiparticles in Fermi liquids? And finally, we're understanding how this many-body energy invariant arises from physically, or why it should exist and give you T-linear resistivity with the same slope across the different physical regimes is also an interesting question. So with that, I end my talk, and thanks to everyone for their attention and the questions.
Thank you very much. Thank you, Aavishkar. Any question from the audience?
Can I ask a question?
Please go ahead. No.
Aavishkar, that was a wonderful talk. So in the Kondo breakdown model, the FL to FL star transition, you said you have a T-linear resistivity with some log corrections.
Yes.
So can you, so where does that come from? Can you explain where that came from?
Okay, let me just pull that slide back up. All right. Yeah. So I mean, that's also, it's basically the same as that, as those disordered interaction models that I was talking about, right? You're in 2 dimensions and you have this random G, except the only difference is that boson couples to C dagger F instead of C dagger C, but one still, like, if one still gets the same kind of boson damping because C and F have Fermi surfaces with some density of states, one still gets a mod omega boson damping from that, and then one gets the self energy that works out like this. Really, there's no difference between having C dagger C and C dagger F because both C and F have the Fermi surface density of states. So it works pretty much exactly the same way.
Oh, wait, so this with disorder, is that?
Yes, yeah, the interactions are disordered, of course.
Okay, so it's not in the translation invariant model.
No, not in the translation invariant case.
Okay. I see. So the story is basically the same as what you explained earlier.
Yes, yeah.
Okay, very good.
Except for this skewness, in the self energy. That's the interesting new thing you get here. Yeah.
Thanks.
Tarun Grover. Tarun.
Hi, Aavishkar. Yeah, very nice talk. Thank you for the talk. I had a question about, maybe it's related to what was earlier asked. So if I consider, let's say, fixed n but large, choose some number and take L going to infinity limit, what do you expect the many-body spectrum level spacing to be? Will it be polynomial in 1/L, or will it be exponentially small in L? My guess is probably 1/L to the power something.
Yeah, it's not exponentially small, certainly, because in this Fermi surface model, we did we computed how the entropy behaves, right, at finite temperature, and we didn't find that there is a non-zero zero temperature entropy. If you had exponentially small level spacing like in SYK, you do get a finite zero temperature entropy, which is absent in this case, so not exponentially small. Yeah.
That only tells you whether it's, it could be still e to the power minus a square root L or something, right? That doesn't tell you whether.
Yeah, so it could be sub-exponential or some different power. So that actually is
just
a class.
To make sure. But I'm still confused. Go ahead.
There is a class of zero-dimensional models that I'm investigating numerically right now, which is, they're not they are non-Fermi liquids, but they're not as extreme non-Fermi liquids as SYK. And in the sense they don't have a zero temperature entropy, but they still don't have quasiparticles.
I got confused by your statement. I thought all your calculations are in the limit where first n goes to infinity and then L goes to infinity. So how do you even know that what is the ground state looks like, right? The spectrum.
Well, yeah, obviously to investigate these low energy spectra numerically, one has to take n finite.
No, I'm not asking numerically. I'm only asking analytically. What do you know about? So I fixed n and take L to infinity. What calculation has been done for that? And I thought all your calculations were first n to infinity and then.
So no, we haven't done any calculation that way analytically, if that's what you're asking.
But then there's no analytical understanding of what is the level spacing as a function of system size L. Is that fair to say?
There is no analytic understanding in that model of what is the level spacing as a function of system size. Yes.
Okay.
Except for the fact that it can't be exponentially tiny like in SYK because there's no zero temperature entropy.
I understand. Okay.
Yeah.
And other question I had, maybe related question. So since you're working in this limit where n is much, parametrically bigger than L, but what is that parametric relation? But how large should n be compared to L for your solution to be valid? Is it, can you say a bit more? Maybe I missed that.
Just hold on. I saw someone saying they can't see my slides. So yeah, okay. I mean, I was, yeah. Right. So, okay. This was just a slide that I was trying to show Senthil related to his question. Okay, but your question is that what is the parametric relation between how low you can go in energy scale and how many 1/n corrections you need to include?
Right.
Is that did I get that right?
Yeah, it's basically the same thing. Yeah. Is there some relation between n and L has to be satisfied so that your solution is?
Yeah, there is some relation that's schematically like that. The exact relation is obviously model dependent, right? In different models. But yeah, I will only truly know that answer once with all these, this 1/n fluctuations are actually computed, right? I mean, like in SYK, they have been computed, at least like Schwarzian corrections, the Green's functions and stuff, and there it is. There is a precise form of that relation. So one has to do that in these models. It's an arduous task, but someone will do it in the future.
But could it be that may miss even? You're calculating some perturbative calculation in 1/n. Can they miss the actual physics in the other limit, L goes to infinity and going to infinity? And large or fixed and whatever. Is it obvious that this just calculating 1/n correction is enough to get the other limit?
The other limit is you're saying the n equals infinity limit.
No, other limit is n is finite. N is large, but finite.
Oh,
and L
you mean is it obvious that adding more and more corrections will allow you to converge as much as you want
right
to low energies? No, it's not obvious.
Yeah, that's not. Yeah.
But I don't know of any way in which there is an obvious answer to your question, right? So this is just a new route we have, and we have to try it. I'm just optimistic that it will work out because, well, it does work pretty well in like SYK, for instance. Yeah.
Okay. Can I ask one more question? Just maybe a stupid question, maybe a remedial question. So in the SYK, there've also been calculation in 2 plus epsilon expansion, where that 2 is how many fermions are involved in a single term of the Hamiltonian. Like, so this is for example,
SYK Q thing, yeah.
Right. So SYK Q, if we send Q equal to 2 plus epsilon, there's some expansion one can do, right? Because Q equal to 2 is basically free. So
yes.
So are there any insights from that in these models, or is that not useful somehow?
These are the kind of things that John McGreevy has been doing, right? I mean, like,
right.
So in these models, there's also like there's this paper by Senthil and McGreevy and Max and Hongliu where the boson propagator is treated in some z equals 2 plus epsilon expansion. Right, one can try to do that one can do this with these large n equations as well, and I mean you get like the same marginal Fermi liquid behavior that they see in that case, and you also get you get like they did some analysis of instabilities and stuff in that paper, and the large n equations give results that agree with what they already had in their calculation. Yeah.
Okay. Thanks. Yeah, I don't have.
Any other question from the audience? Oh, sorry. I think we should thank Aavishkar first. Aavishkar, Dhanyavad. Thank you very much. Great.
Okay.
If you have more questions, you can stay and ask. Thank you.